So, mass action expression, we're going to do a couple. We'll just do some calculations really quick. So, we're going to look on page 517. And what I want you to do is the two experiments. I want you to, the first two rows here, you're going to create a equation or a equilibrium expression using the chemical equation on the top of page 517. It is N2 plus 3H2 gives you 2NH3. Okay, so what you're going to do is you're going to take this equation, which is N2 plus 3H2 gives you 2NH3. And then you're going to take the numbers of experiment, and we're going to look at, you guys take the equilibrium concentrations on the experiment 1, you guys do experiment 2. Okay? And then I'll do experiment 3. So set up your expression and then plug your numbers in and get a calculated value. So we're doing table 13.1, you're taking those concentrations, you're plugging it into the expression, and then you're getting a final answer.
Good afternoon, BHS. Sorry for one more interruption. We will be having Southern High.
So then when you take these numbers in and get your expression, again, these are experimental values at equilibrium. And then once we put them in our equilibrium expression, we're going to go ahead and square the top one, and the bottom one we're going to cube the 2.77 and multiply it by 2.59, and then this is the answer you would get when you plug those into your equilibrium expression or mass action expression. Okay. So on this, we're going to be finding what we call the reaction quotient. So we're going to plug those in. So that's what? NH3 is 2.5 squared. N2 is just 2. And then we got 2 cubed. Okay, what'd you guys get for an answer? An answer? 0.39. Okay? So 0.39, it doesn't have units. Now, any questions on that? So, is this at equilibrium, this reaction where we take those values? Is it at equilibrium? No. It's not at equilibrium. Because at equilibrium, it has to be 0.0602. And it's not at equilibrium. So, let's see where it's at. Does it need to react? Do we need to have more of the reactants react? So I'm going to put this reaction up here again. It's H2 plus N2. H3. We got 2. We got 3. Okay. So according to this is bigger than our constant, right? So if it's bigger than our constant, what we have is we have more NH3 than we do value of NH3 is greater than our reactants. Do you agree with that? So guess what? If we have more of NH3 than the reactants, which direction does it need to shift to get to equilibrium? Because all of these will eventually shift to get to equilibrium. Meaning, eventually this reaction, if we let it keep going, will shift to where I can get 0.0602. So is it going to shift and go left, which means it's going to make more reactants, or is it going to shift right where it's going to make more products? Which way do you think it's going to have to shift? Left, right? No. Left, right? No. No, left. Correct? Left.
Just give them.
So it's going to shift left. Everybody agree?
Right.
No, left. This is Abbott Costello, right? If this number came up to be, really small, like something to the minus third, like 0.003, then it's going to have to shift to the right to make more products so it gets into equilibrium. So we're going to do what's called the Chatelet's principle next week, and basically we're going to take these different substances and we're going to change their conditions in a way that they shift left and right. They'll make more product or more reactant. But this one's going to have to, it's going to have to be the point where it's in this mode where this arrow going backwards is going to be bigger. And it's going to be bigger until what? Until it reaches equilibrium, the 0.0602. Okay? All right. Questions?
We have this posted online.
You know what? I'm not going to give an assignment because we're going to do a little activity here now because we don't have enough time and we're going to be taking off about 20 minutes. So good luck.
Thanks. Good luck.
Questions? So you guys now have the opportunity. You can take an equation. You can write the equilibrium expression like this. And you can calculate it. And then if you got multiple experiments, you can calculate multiple experiments. And then if it says the constant should come up to this, then you know if it's in equilibrium or not. And if the value doesn't come up to, for in this example, 0.06, we know it's not in equilibrium, and we can tell which way it's going to shift. This one's going to shift left. If it's going to be smaller, it's going to shift right. So if it's bigger, it shifts left. If it's smaller, it's going to shift to the right. Okay? And you guys will kind of know more about that in a little bit. So now we're going to take an opportunity to do a little bit of an activity. You've got to get your periodic table out, and you've got to turn it to the side that does not have anything with the atomic numbers or atomic masses.